So, let us continue with our discussion of the algorithm for computing minimum spanning trees in a distributed system. We were looking at Gallagher Moonlit Spira algorithm. So, we will quickly recapitulate whatever we studied in the last class and then complete the algorithm in this class. So, remember that in this algorithm we start with each node as a one node fragment, where the meaning of a fragment is a subtree of the minimum spanning tree. So, initially every node is a single node fragment, and the nodes in a fragment at any point in the algorithm cooperate to find the lowest weight outgoing edge of the fragment. And once the lowest weight outgoing edge is found, the fragment which is at a lower level combines with a fragment at a higher level, or two fragments at the same level combine to form a fragment of the higher level. We had seen that the rules for joining two fragments was like this, that if for a fragment f, Ef is the lowest weight outgoing edge from the fragment, then if the edge Ef leads to a fragment f dash, then the joining will take place provided that the level of f dash, namely L dash, is greater than L. Then the joining will be allowed by rule A, and when this happens, then the smaller fragment, namely f, will inherit the name and the level of the higher level fragment. And we had seen that all the parent pointers in the fragment at the lower level will now be oriented towards the core edge of the fragment at the higher level. If the two fragments which are joining, namely f and f dash, are in the same level, that is L equal to L dash, then they join by creating a new fragment of level L plus 1, and the name of the new fragment is the weight of the core edge. The core edge in this case is the edge Ef, which joins the two fragments at level L. And then again the nodes in both f and f dash must reorient their parent pointers in such a way that they point to the core edge Ef. Okay. And whenever a fragment attempts to join with a fragment at a lower level, then the fragment of the higher level must wait until the rule A or B applies. So, this was what is the summary of the strategy. Then we looked at the algorithm code, we started looking at the code, and we saw that at the beginning every process must execute this piece of initialization code, and what essentially is done here is, this is where the node behaves like a single node fragment. So, for a single node fragment, the task of finding out the smallest weight outgoing edge is simple because it is incident on that node itself. So, the process P actually finds out the channel with smallest weight and declares that channel to be a branch edge of the minimum spanning tree, and it sets its own level to 0, its own state to found, and this is a counter which we have not yet described what it does, and then you send a connect 0 message to the neighbor q. Okay. Then we saw, in general, when a node receives a connect message, it checks whether the process from which it receives the connect message has a level L which is lower than its own level or higher. If the level L is lower than its own level, then this is a case of a lower level fragment trying to connect to a higher level fragment. So, by rule A we allow that, and therefore, the process P declares the link from P to Q as a branch node of the tree, and then sends a initiate message to Q, and the role of this initiate message is to reorient the parent pointers of all the nodes in the fragment of P to point to the core edge of the fragment to which this P belongs. Okay. So, it sends this initiate message to Q, so that every node in the fragment belonging to Q inherits the level P, inherits the name P, inherits the state of P, and also reorients the parent pointers to point to the core node of the fragment to which P belongs. If it finds that the level of the connect message is not smaller than its own level, then there are basically two cases. One case is that the level is equal, and the other case is that the level is greater, and if it is greater, then we know that it has to wait. So, if we find that the link so far between P and Q is still basic, in the sense that we still have not declared it to be a branch or a reject edge. So, then this is a case where a larger fragment is trying to combine with a lower level fragment. So, we just process the message later. Otherwise, this is the case where two fragments of the same level are attempting to join. So, we do the following thing. Now, how do we know that this is the case where two in the same level are trying to join?
We saying that both of them would have found the same edge and would have sent an initiate message and changed the status to branch.
Right. Both of them would have sent an initiate message to each other after changing their status to branch, and therefore rather connect message to each other, but after setting that link to branch. So, therefore, they will see when they receive this connect message, this one will see that it is not basic anymore. Okay.
But is it necessary that both of them will, when the levels are same, they both, the minimum edges, that is EF will always be EF dash?
Yes, it will always happen. If the if the levels are same, if they are at the same level, and this has sent you see, if you look at it this way, that if you look at this fragment as one part of the network and the remaining as the other part, then obviously this edge has to be the minimum weight edge of that. See, as long as that does not happen, we will not allow these two to join. See, okay, that is a good question. So, just let me draw this. So, you see, suppose this is a fragment at level L, okay, and this is the minimum weight outgoing edge, right, and it leads to some other fragment, a node in some other fragment, okay, which is also at level L, right. So, this one sends a connect message, right. Now, we will not allow this one to join until this one also feels that this is the minimum weight outgoing edge, right. And why are we not going to allow that?
Because it's not its minimum.
Now, see, this edge is definitely going to be, this edge is definitely going to be an edge of the minimum spanning tree. Why? Because if you take any fragment, the least cost outgoing edge from the fragment always belongs to the MST. So, this edge is also going to belong to the minimum spanning tree, right. But at this point of time, we are not allowing this to join. But at some point of time, you see, if I look at this as one, if I partition the set of nodes as those which belong to this fragment and the rest, then the best bridge between this and this is this one, right. So, eventually at some point of time, either this one will join with other fragments etc., and maybe create some other fragment, and then at that point of time there are two possibilities, either it is still at level L or it is at a level L which is higher than that. As soon as the level of this one becomes higher than that of L, it will respond by rule A.
So, whether it is setting it to be a branch, because both are equal and both send connect messages to each other.
Whenever both of them are sending connect messages to each other, at that point of time we allow them to connect.
The Gaussian branch is this edge is not being set as a branch at that point of time.
The edge is
Not being set as a branch.
when you send the connect message at that time.
Only if it's less than it is sending as a branch.
No, no. When we come to the place where you are sending the connect message, you will see that it will set it to branch. See, this is being set because this one did not send a connect message. Okay, just look at this case. See, before you send this connect message to Q, okay, you have set the channel PQ to branch. So, the sender of the connect message always sets this to be branch. Okay. The receiver will set it to be branch only when rule A applies, and when rule B applies, at that time this one has also sent a connect message to the other side. So, then it has set its that link to be branch. Alright. So, if you look at the joining rules carefully, you will see that if EF leads to a look at rule B, if EF leads to a fragment F dash with L equal to L dash and EF dash equal to EF. So, the least cost outgoing edge of both F and F dash is the same, then they combine. Okay. I should have highlighted this thing earlier. See, this is another condition that is there in this rule. Okay. So, that is why when you get when you check this, if this process has also sent a connect message to Q, then the status of the channel from P to Q will not be basic anymore, it will be branch, then rule B will apply, and when rule B applies, then symmetrically both P and Q will send initiate messages to each other, right. So, this sends the initiate message to Q, except that now the level has increased. So, it is level P plus 1 and the code edge is now WPQ. So, the name of the code edge becomes the name of the fragment, okay. And we set the state to find, because again in the integrated fragment we need to find out the minimum cost outgoing edge. And then we saw that when you receive the initiate message, then what you do is you basically propagate the wave. So, the initiate message propagates like a wave down the fragment along the branches of the tree, right. So, every node which receives an initiate LFS message from Q, it will set its level to L, its name to F, its state to S, okay, and make its parent pointer point towards the node from which it received the initiate message, right. These are things that we will use to determine the best cost weight, okay, and then after that we, for all neighbors of P which are on the tree, okay, except the parent, we propagate the initiate message to all those children in the tree, okay, and then you check whether the state of the fragment is find. If it is find, then it starts the test procedure, and test is the algorithm that is going to test whether an edge is in the same fragment or not, okay. Now, what did we see here? We saw that, did I go through the code of test in the last class? No. Okay. So, let us start straight away from that point. This is the test procedure. So, when is the test procedure invoked? It is invoked by a node which knows that it must now participate in the search for the least cost outgoing edge. So, what it does is, it starts, the node starts by looking at the edges incident on it. So, at any point of time in the algorithm, there are three types of edges incident on it: edges which are already in the tree, they are branch edges. No point trying those edges because they are already in the tree. There are edges which are reject, those edges are already between nodes in the tree, in the fragment, right. So, they cannot become part of the tree at any point of time. So, again we do not need to test them, it is only the remaining ones that we need to test, right. So, among those remaining ones there are some of them are edges which are leading to other fragments, really leading to other fragments, and edges which are leading to the same fragment, but we have not previously discovered that. Okay, these are the two types of edges which are still labeled as basic. So, it is going to try, what it is going to do is it will find out the minimum cost among these and first test that, right. So, if the test succeeds and you realize that this is a edge leading to another fragment, then you have already found the best edge incident on you, right. But what you need to do is not only look at the best weight edge incident on you, but also on the best weight outgoing edge incident on any of your successors in this subtree, right. And how is the subtree oriented? It is oriented through the parent pointers and points to the core edge of the current fragment, right. So, what the node will do is it is going to wait to get updates from all its children in the tree before it sends its decision to its parent. The decision, what are the contestants for the decision? Its own minimum weight outgoing edge and minimum among the outgoing edges of all its children. So, it will take the minimum of this whole set and then pass it on to its parent, saying that look, in my subtree this is the least cost outgoing edge, right. And to count that how many of those I have received, we will use that RECP, okay, because every node must wait to get updates from all its children before it passes it to its parent, right. So, this is the, let us now look at the code. So, first of all we need to test whether there is a neighbor which is still unexplored. So, it first checks this thing, this is checking whether there is any edge which is still not reject and not branch. So, then what it is going to do is if there exists such an edge, it will set test CH, the test channel, to be that queue for which this is still an unexplored edge and WPQ is minimal, right. In fact, it is going to be minimum because you see that all edge costs are different, right. So, among its basic edges it will choose the one which is minimum and the node to which it leads will be called test, will be saved in test CH. No, here we just checked whether there is such a neighbor, and so we checked whether there is such a neighbor, okay. If there is such a neighbor, then among those neighbors we choose the minimum one. So, this one actually, this line expresses that among these neighbors, okay. Is that clear? Then we send a test message to the node that we have selected with the level of P and the name of P, okay. And if there is no such neighbor, then we just set test CH to be undefined and then we report, okay. If there is no minimum,
one of the edge among the incident edges will be the minimum edge.
Yes.
So you said if there is no edge minimum means.
No. You see, but this condition is important, that you have to have an edge which is not yet explored. If you have already seen that all your incident edges are either in the MST or not, or known to be not in the MST. So they are either branch or reject. Then there is nothing that you can do at this point of time. Okay. Now this report is another procedure which we will come to shortly. Okay. That reporting procedure is actually going to collect all these information from the node and its children and then pass it on to the parent. Okay. Now let us look at what a node does when it gets a test message from a neighbor. If it finds that the level of the test message is greater than its own level, then we do not do anything, we just defer. Why do we defer? We remember in the last class we discussed this case, that it is possible that the level of the fragment to which P belongs will increase. Why? Because they are actually in the same fragment, but the initiate message from the fragment to which P belongs has not yet to which Q belongs has not yet reached P. Okay. So in that case this must wait, because if it now allows it, if it now says that this is a outgoing edge, then you might inadvertently put in an edge which creates a cycle, right. This is also the reason why we want to have that partial order, allowing only fragments at a lower level to join with fragments at a higher level, right, so that we do not create cycles. Okay. If f is equal to name P, so this is the else part. So now we have checked that L is not greater than level P, so it is either equal to level P or less than level P. Then what we do is we check if f is equal to name P. If f is equal to name P, then they are in the same fragment, right. So what you do is you check whether this is basic, right, then you set it to reject. Okay. What, how is it possible that this may not be basic? What else can it be? Can it be branch? It cannot be branch, because a fragment declares an edge to be a branch only when it is sure that it will be in the MST, right. In this case this cannot be in the MST, right. So it is not, it cannot be a branch. Can it be reject? It can be reject. How?
When it's all are in the same fragment, the one of it will be minimum.
What could have happened is that both discovered that this is a reject at the same time. So then it can be reject. Now can it be?
The P would not have sent a message on it.
See, when it is sending a test, at that point of time it is not going to be reject, because if it is reject, why will it send a test, right. So if it sent a test, then it must be the case that at that point of time it was basic, right. All right. So just think it over, what can it be? Why did we put this?
Message from Q must not have rejected, may not have reached, but it would have sent a test message, but then it would have got a message and understood that it is reject.
But what will that message be? I mean, how will it know that it is reject?
Test message from the say other node also. Q also sending a test message.
Right.
Then it could have discovered it's a reject. It also
Right.
sends a test message. The Q also sends a test message.
If Q has sent a test message, this is that test message. This is that test message. Right. So, what could have happened is that it sent a test message and got a reject in answer. Right. Okay. And this node got the test message from Q after it got the reject message, because of the, we are not assuming FIFO channels, we are not assuming that it is FIFO delivery. Are you getting my point? See, what is going to happen is that it is quite possible that both of them send test messages to each other, right. Now, for this node, when it sent the test message, the other node had already sent its test message. Now, this one, after getting the test message, sends a reject, and the reject reaches this one earlier than the test message arrives, right. So, when it gets the reject message, it has already declared that channel to be reject, then it gets the test, right. Anyway, these are finer points, not so important. I mean, but if you want to really write the code, you have to understand that this can be possible. So, it checks whether it is basic, then it sets it to reject, okay. And if Q is not equal to test CHP, then it sends a reject to Q. Now, what does this is that optimization that we talked about in the last class, that if P has also sent a test message to Q, which means that test CHP is Q, then we know that the other side will automatically realize that this is a reject message. So, we do not need to send another reject message, right. So, only when Q is not equal to test CHP do we send a reject message to Q, okay. And the other option is that if Q is not equal to, if Q is equal to test CHP, then we have to test. Now, what does this mean? No, see, in a distributed algorithm, everything is initiated by the receipt of a message, right. Now, when a node discovers that its previous test has failed, right, that edge has been marked as reject, right. Now, it must again resume its test because there are other neighbors, right. So, it again resumes the test, but this test is going to throw up a different neighbor than the previous time it did it, because now that neighbor has become, now that edge has become reject or whatever, right. So, it is not going to pick up the same edge once again, okay. So, this test is actually telling the node P to resume its search for a minimum cost outgoing edge, alright. Now, this is the case where we found f equal to name P, okay, and we decided that it is an internal edge. If f is not equal to name P and the level of L is less than level P, then this node allows that edge, this fragment allows the edge. So, it sends an accept to Q, okay. Now, what happens when an accept from Q is received? We do the following thing. When we get an accept from Q, the local search for an outgoing edge is done. So, the node has already found an edge, outgoing edge from itself, right, and because we are searching in the order of increasing weights, so this is the minimum outgoing edge from P. The moment you receive an accept, you have discovered the minimum cost outgoing edge from that node, because we were testing the edges in increasing order of weight. So, the first one which turns out to be an outgoing edge is the minimum outgoing edge from that node, right, but we still have to collect the best cost from the children before we pass it to the parent, right. So, let us see what we do. We compare this WPQ, the edge cost of this, with the best P. What is best P? It is P is the best that P has seen so far, that includes its own and its subtree. Okay. Now, if it finds that this is lesser than that, then it has found a better candidate. So, what it does is it sets best weight P to be equal to this WPQ. Okay. It sets best CHP to Q because it has got it from Q. Okay. And then it calls this report procedure. Remember that this report procedure was called earlier also. That is the one which is going to collect everything and pass it to the parent. Okay. What do we do when a node receives a reject message? It checks whether the status of the channel from P to Q is basic, then it sends it to reject and then resumes its test, because it again has to find another least cost outgoing edge. Is that clear so far? Now, reporting the lowest weight outgoing edge from the fragment. Now, the lowest weight outgoing edge is reported using the report procedure that we are going to see shortly for each subtree using report W messages. Node P counts the number of report W messages it receives using the variable rec P. Okay. The report W messages are sent in the direction of the core edge by each process, because that is how the tree is oriented, and the messages of the two core nodes cross on the core edge. Okay. We will see how that happens, and both receive the message from their father. So, what is happening is, you see that here is the core edge, and this is one fragment, this is one fragment joined by the core edge to form the integrated fragment, right. Now, this fragment, the best weight outgoing edge of this fragment comes up to one end of the core edge, this one comes to the other end of the core edge, and then they exchange. At this point they know which is the minimum cost weight, both ends of the core edge know. Now, if it is on this side, then this one now starts doing the needful to reorient everything, so that you can send a connect message from that. Let me draw it. So, suppose this is the core edge. Remember that the whole tree is oriented so that all parent pointers point to the core edge, right. Now, suppose, so all the best weight of the least outgoing edge of this fragment gets reported here towards this core edge. Similarly, all the best weight from this fragment for the outgoing edges gets reported here. Then these exchange this. Now, both this P and Q knows which is the minimum. Suppose, without loss of generality, it is on Q, it is in the fragment, it is on the subtree rooted at Q, right. Now, what should happen? The node from which that outgoing edge is there, this is the least cost outgoing edge, should send a connect message. So, we have the Q will now propagate the information down towards this node, right, and then this is going to send the connect message, right. And if this is, this becomes, this is, these are two at the two, these two are in the same level, then this will become the core edge. So, all the pointers will now then in this one they will all reorient in this direction. Okay. Now, see these do not have to change because they are already oriented in that direction, right. Huh? So, let us see how
core nodes will also reorient themselves because this PQ is no more
these ones, yes, P will reorient itself towards Q in that case, provided that this becomes the new core edge. It may not always become the new core edge. If this one has a level higher, if this one has a level which is smaller than this, then also it will have to reorient. Why? See, this is interesting. See, this may not become the core edge of the integrated fragment. There are two possibilities. One is that these two are in the same level, in which case this one will become the core edge. So, all of this will have to orient towards this. Otherwise also this will be allowed only if the level of this fragment is greater than the level of this, right. So, then only we are going to allow this one to join into this, and in that case the core edge of L, wherever it is, that becomes the core edge of the integrated fragment. So, in that case also all of these will have to orient towards this, because this is the edge through which it reaches the core edge, right. So, this reorientation will have to be done anyway. Is it clear? So, let us look at this now. The report W messages are sent in the direction of the core edge by each process. The messages of the two core nodes cross on the edge, both receive the message from their father. When this happens, the algorithm terminates if no outgoing edge was reported, otherwise a contact L message must be sent through this edge. Okay. Now, let us see how, let us go through the code, and then the tree must reorient. So, I have already told what this does. If an outgoing edge was reported, the lowest weight outgoing edge is found by following the best CH pointer in each node, starting from the core node on whose side the best edge was reported. And then a connect L message must be sent through this edge, and all further pointers in the fragment must point in this direction. This is done by sending a change route message. So, after the connect message is sent, the node sending the connect message starts by initiating a wave with the change route message, and the change route message actually changes the orientation of that entire fragment to point towards the new core edge. Okay. So, this is the report procedure. What does the report procedure does? It checks if the number of see what is it checking? It is checking the number of nodes, okay, such that the status of Q is branch and Q is not equal to further P. If it has already received that many number of report messages, and if test CHP is undefined, which means that its own search, local search has concluded. See, this is the indicator that its local search has concluded. Then its state P is said to be found, because it has already found out the least cost outgoing edge in its subtree, and it sends report best weight P to father, right. How long does it wait? Until it has received the report messages from all its children. So, all the branch neighbors except the father, right, and it has checked that its own search has completed, then it sends the report of the best weight to its father, right. Okay. And what about its the the pointer towards the best outgoing edge. The best outgoing edge can be a local edge or it can be an edge through any of its children, right. So, that will be captured by the best CH pointer. The best CH pointer will either point to the node in the other fragment or it will point to a child through which the best least cost outgoing edge can be reached. Okay. Now, let us see what do we do when a node receives the report message. It checks if q is not equal to father p. Okay. If q is not equal to father p, then it is receiving it from a child, right. If it is receiving it from a child, then it checks whether the reported weight is less than best weight p.
The child would obviously not be sending any report message around this.
Child?
Father would not be sending a report message.
No, only in the top that will happen in the core edge. In the core edge, this will send to this will send to this. So, they will, both of them will receive this thing from their father, because for the core edge q is the father of p, p is the father of q. Right. Now, what is happening here is that if q is not equal to father p, that means it is getting it from a child. So, it checks whether the weight that it has got is less than its current best weight. If so, then it revises the best weight to this and the best channel to q. See, this is a pointer which points to the child through which the best can be reached. Okay. Increments RECP and again executes the report. Why do we execute this again? Because we need to check whether this RECP has reached the desired number, in which case we need to send a report message to the parent. So, every time we get a report message, we again execute the report procedure to do that check. If q is father p, then pq is the core edge, right. And when you have found, when you are in the core edge, then you check if state p equal to find. If the state p is equal to find, that means that your own subtree's search has not completed. Suppose the fragment under p completes first, then p will send a message to q. Now, q will get a message from its parent, but can q take a decision right now? Not yet, until its own fragment has completed, its own subtree has completed, and that is indicated by this. See, when a node and its subtree is done, then we change the state p to be equal to found, remember. So, if it is still find, then that means that p's subtree evaluation is not yet complete. So, then we process this message later. Otherwise, if this is found already, then we check if the one which I am getting from q is better than my own, or rather worse than my own. If it is worse than my own, then the least cost outgoing edge belongs to the subtree of p. So, now the q side will not have to do anything at all, right. The p side will have to do all the work. They will have to reorient to point towards the outgoing edge, and the outgoing edge will have to send a connect message, right. So, if w is greater than best weight p, then this change route is initiated. Change route is going to do that reorientation, and the last case is if w is equal to best weight p equal to infinity, then we have reached the termination of the algorithm. When can this happen? When both the fragments reported we do not have any outgoing edges. In that case, the weight that will be reported will be infinity, right. So, what I have got from p subtree is also infinity, what q has given me is also infinity. So, there is no outgoing edge. That means we have complete, there is only one fragment now. So, we have found the MST, that is where it stops.
So, how does best channel p is equal to
here. See, we set this base channel P equal to Q, so that you remember that along which child you got the best weight.
But how will it maintains about whole fragment that from the whole
The Q will again maintain its best CH Q. So, you will just follow the best CH pointers from parent to child to child to child. Okay. That is what we will do now. What is the procedure change root? You check if the status of the channel from P, okay, this is executed by P, for base CHP is branch, right. What does this mean? If it is branch, then it is in the same tree, then we just send change root to the child. This part is sending a change root to the child because we saw that the best channel is a channel on its own subtree. So, it just sends a change root to its child. If it finds that it is not branch, that means this is a edge to the some other fragment, right, and therefore, this is the new edge that we have discovered. So, then what it is going to do, it will send a connect level P message to base CHP, right.
Why would the state of best channel P be equal to branch?
This one,
First condition.
you see, if it is branch, that means that the base channel is a child in the same, is along a child in the same tree.
You discovered a best outgoing edge.
See, but the best outgoing edge was reported by somebody down here. All the nodes in the tree above that, they know that it is down there somewhere. So, this change root will have to propagate right down there, and then the connect message will be sent here. Okay. Now, the change root messages are going from parent to child here.
So the branch is connecting one fragment or another.
That's when you find that it is not equal to branch. That means that this is not yet part of the subtree, but this is your best channel. So, this is the best weight outgoing edge.
Branch would be only when you have a core, there is a core edge. P to P or no?
Okay, because we are running out of time, I want to finish this straight away. Okay, I will take your question after the lecture. Okay, now look at this, that we send this connect level P to base CH and then set this to be branch, because now that we have sent a connect message, this has become part of the MST, right. For all other nodes, whenever they receive a change root, they will just execute this change root procedure to do the needful. Okay. Is that clear? Right. A quick look at the complexity of the algorithm before we terminate. That this algorithm computes the minimal spanning tree using at most 5n log n messages plus 2e messages, right. Now, look at the edges which are rejected. For these edges, it is an edge, once it is rejected, it is never considered again. So, it is rejected at most once, and this requires 2 messages, because we need to send a test message along that and get a reject message. So, this accounts for at most 2e messages for the reject ones. Okay. For the ones which are not rejected, namely the branch and the basic edges, we look at each level. At any level, a node receives at most one initiate and one accept message and sends at most one report, one change root or connect message and one test message not leading to a rejection. Okay. This accounts for 5 messages per level, and for log n levels this accounts for a total of 5n log n messages. So, that gives us this figure 5n log n plus 2e. Okay. So, we stop here, we are at the end of this chapter on minimal spanning trees. and whatever questions are remaining, I can take it outside the class, because there is another class going to start right here.